Thank you, and welcome for joining my session on real-time machine learning with Pulsar Functions. My name is David Kjerrumgaard. A little bit about me. So in addition to being a developer advocate at Stream Native, the company behind the open source Apache Pulsar project, I'm also a committer on that project, as well as author of the upcoming book, Pulsar in Action by Manning Press. Let's begin this discussion with an overview of the machine learning model development process itself and how Pulsar functions fit into that overall process. So as you can see from the slide here, that the machine learning model development lifecycle really consists of 5 separate phases that occur in an iterative process. It begins with problem identification. Specifically, what is the business problem we're trying to solve when using this machine learning model? What is the intended goal that we're trying to achieve? Once we've refined that process, the next step is to begin the data acquisition phase, which is data extraction, exploratory, and analysis. You want to look at the existing data sets you have available to you and how you can sort of massage those data sets in order to generate features and different data that might be interesting to feed the machine learning model. Once you've gone through that exploratory data analysis phase, the next is the development of the machine learning model itself. That's the process of feature engineering, which is extracting the exact features you want to deploy to the model, as well as building the model and beginning the validation process of the model itself. After the development phase, then comes the training phase, where the machine learning model that you developed is then trained and tested against realistic data, oftentimes production data, in order to compare its accuracy against the predictions it makes versus the expected results. This is a lot of where a lot of the work occurs. It's a very important step. Finally, once the machine learning model has been trained sufficiently and it's ready to be released to production, the deployment phase occurs, and that's when the machine learning model is deployed. It is this phase here, which is what we'll specifically focus on as far as machine learning model deployment using Pulsar functions. But it's good to have an overview of the entire process, and we'll walk through the process throughout this talk. So let's start with the model deployment phase. That's the ultimate goal. So once a model is developed, it can be deployed to operate either in batch or real-time mode. Batch mode, the predictions are generated on a recurring schedule and then stored in a database. So it's something that you can run periodically and do predictions, shopping cart analysis, things of that nature. Those things can be done statically with existing large data sets. In contrast, real-time machine learning model refers to the process of generating those predictions on the fly as the data arrives, because we need the information to be up to date in order to make an accurate prediction. Consider the estimated time delivery use case that is used to generate a prediction of when a food order is going to come whenever you place an order on a service such as Uber Eats. It's impossible to generate a batch of those estimates beforehand. And so that's the use case where real-time machine learning model deployment is the only real solution. So let's begin and walk through the process with problem identification. What is the business problem you're going to try to solve today? In our case, we're going to do the delivery time estimation model for a fictional food delivery service. So when a customer places an order, we want to provide them feedback on their phone of an estimate of when their food is going to be delivered. And we want to give them an accurate estimate, right? Just so a good customer feedback experience. But in order to make that prediction, we need to really predict 3 separate things, right? How long is it going to take the restaurant to prepare the food? How long is it going to take the driver to pick up the food after that it's been prepared? So that transit time for the driver from where they are to that restaurant itself. And then how long it's going to take the driver to drive from that restaurant once it's picked up the order and ultimately arrive at the customer's location. You need to identify and predict all 3 of those things in order to get an accurate estimation. But why is that problem difficult, right? There's basically 3 parties involved in every delivery that are dynamically paired together. So we can't pre-compute all these predictions for all possible combinations, right? It's an NP-complete data set. We don't know which restaurant's going to be chosen, which driver's going to be chosen, and where among all our customers are going to place an order when they're going to do it. And even if we could theoretically generate such a batch prediction, it really couldn't account for real-time conditions such as traffic conditions, how busy a restaurant is, what's the lead time on preparing a meal at that restaurant at this given time of the day, etc. So all this tells us we have to make these predictions in real time. There's really no way to do any sort of batch processing around that. So once we made that decision, we know what we're trying to solve. Let's look at the data acquisition phase. What data do we have available in order to use with our machine learning model to make these predictions? So again, what data do we have? Well, there's a relational database out there that keeps track of the different life cycle of the food order itself, right? So there are 3 different actors again. When a customer places an order, that gets entered into the transactional database and the time that was placed. Then when that order has been assigned to a restaurant, it updates its status and says, you know, I'm processing this order, I'm this restaurant, and it acknowledges it. And so that information can be tracked for payment and things of that nature. And also we have the drivers with their mobile apps, you know, plugged in. So not only are they giving us real-time information around their positioning, which is shown there at the top, where we put the data into real-time caches, eventually into the data lake for further analytics. But we also have when they acknowledge an order. So we'll solicit them to pick up an order. If they say, yes, I'm going to take that order, they give updates on, you know, they're en route to pick it up. I picked up the order, and then I've delivered the order as well. So all that goes into 2 large data sources. We have a data lake, some caches in front of that to do real-time analytics on the driver positioning. And we use that also to feed the user interface. And then there's a transactional database that can track the food order itself. So we start looking at that transactional database, and we can see that we can come up with some pretty interesting metrics right out of the gate. So we can calculate things like the average meal preparation time, for example, right? So you can run a query and identify, for example, how long does it take, you know, the average difference between the ready time and the place time for food orders by a restaurant ID. And do it also over certain fixed time frames, right? So we can do it, what's their average time on Wednesdays between 11 and 1 p.m., or we can do more relevant recent stuff like what are they doing in the last hour, right? Based on what's their volume, are they starting to increase the amount of time it takes to prepare an order, or is it taking less time? And all that's available in that data set. Another interesting metric we can see is the average meal preparation time by menu items. So not all menu items take the same amount of time to prepare. If you have a fast food restaurant such as McDonald's or Burger King, it's probably pretty close. But if you're dealing with a more traditional restaurant that's doing takeout orders that you know deals with steaks or you know things of that nature, those things that take a significant amount of time. So again, we can do the same analysis, this time also including the menu item ID to get sort of a final grain prediction around based on what the item the customer ordered as well. Another thing that we can get from the transactional database is the average meal pickup time. And this is basically the time between when the restaurant says, hey, the order is ready for pickup, and when the driver actually came in and acknowledged that, hey, I picked up the order. A lot of these things is to capture things around how hard it is to, you know, how close customers are, or drivers are to the restaurant itself. What's the handoff process itself? Is it a very streamlined process where they can come and pick it up? Or do they have to wait in line with all the other customers in order to stand up, come in and say, yes, I'm here to pick up this order? And how does it capture that sort of process? That information is all available as well. And we can drill down into the specific restaurant ID information, so we can calculate that information as well from our data sets. But obviously, what are some of the data sets that we're missing, right? That's part of the data acquisition process. Well, as we mentioned earlier, there's 3 parts, right? There's the meal preparation time, there's a pickup time. The biggest missing part is obviously the driver delivery time, right? So even though we use SQL to produce a lot of these metrics, we can't compute averages on those 2 aspects. The real missing part is the driver delivery time, right? And since we can't know the delivery address or the driver's location in advance, we can't really use historical data to calculate average travel times. I mean, if we could, there'd be many possible combinations or not enough data, right? If a customer places one order one time and that took 30 minutes, that will skew your results if that was a one-time thing. So we really don't have a really good data set for that. You can't really use existing data sets to calculate that data or make an accurate prediction on the travel time. So how are we going to address this problem, right? So one option would be to rely on a third-party service to calculate these values dynamically, right? You could make a dynamic call out once you had the driver location, or you could specifically say from the restaurant location where the driver's leaving to the customer's location, and submit that to like a Google Maps API and give you an estimate of what the travel time is. But that wouldn't be the best approach. Some of those drawbacks to that would be that's obviously very expensive to use that service, even because they It's a metered service. The more you use it, the more you have to pay. And you're also depending on an external service to provide one of the core features of your product, right? And if that service goes down or backs up or decides to change their API, there's going to be changes in your product that are going to trickle backwards. So it's really not the best approach to use that sort of thing. Also, making that external call introduces the possibility of high latency or failures, right? So the customer places an order, click on the phone, they want to get that estimate really quick. They don't want you to not be able to provide an estimate because the Google or third-party API, the mapping API that you're using went down. So it's just another risk that we really don't want to take. So let's look at another approach to doing that rather than a real-time system. And that approach would be delivery time estimates using approximation, right? And also we look at, Uber has an open source project known as H3 that it uses to provide transit time estimates for its rideshare application. So obviously we look at this as a use case, something we could leverage inside our food delivery system as well, using our data set to get us similar estimates, right? So this H3 library breaks a region into multiple hexagons, and it provides an API where it allows you to, if you give it a lat long pair, it will return a specific grid cell. And so you can sort of shrink your space from a point to point to hexagon sort of problem. And then once you've mapped these hexagons onto a large mapping region, you can quickly recalculate the distance, the average travel time between the fixed point of the restaurant and nearby surrounding hexagons, up to a certain diameter, whatever you think is an appropriate radius. But then you can quickly say, okay, that allows you to map. So if a customer location is in one of these hexagons with a lat long, you quickly get that value. You can do a quick lookup into this table and say, okay, for that grid, for that particular hexagon from this restaurant is an average travel time of 12 minutes or 5 minutes or whatever, so on and so forth. And you can continuously update these values as the data comes in from the driver location as well. So it's constantly updated in real time. It gives you more accurate estimation and a real-time view of the traffic flow in and around the city and specifically that restaurant itself. So now we've completed the data acquisition phase and have all the data we think that's available to feed our models. Let's go ahead and look at the model development process itself. At a 10,000-foot view, since we're not data scientists, we're data model deployers, data scientists perform this task using any variety of programming languages and model types. On the left-hand side, they basically have a list of things called features. And those are just basically input values that are fed into the model itself. And on the right side, they have the model itself. So they go hand in hand. I have this model that has 15 different values I expect. The way those values model interacts is really up to the machine learning model itself. And at the end of the process, you're given two things: the model itself and the feature vector definition that you have to fill. Now, from a machine learning model development standpoint, the data scientists can use any variety of languages and toolkits they want. And our goal as deployers of machine learning models not to limit their restrictions in any ways, but rather have an approach that's as inclusive as possible to support all these different model types that they might use, right? So our goal is to allow data scientists to use any combination of these that they want based on their judgment and expertise to solve the problem at hand, and have a framework that allows them to use these models, right? We won't say we can't support this type of model or this programming language. We want to be as inclusive as possible. So once they've chosen their toolkit and language of preference, next they can go on is to the big step is feature engineering. Right, so once they made that decision, they're going to go through a process of deciding, okay, I'm going to start with a certain set of features, and they'll add it to the model, and then they'll test it to see if it gets accuracy as well. So that's an iterative process through trial and error, and again, judgment and experience. That they decide these are the input vectors we need. This is the feature we need. And for our delivery time estimate model, some of the features that they decided upon were average meal preparation time, again calculated from that data set that we saw earlier, the meal pickup time, and then the transit time between the restaurant. Those are some of the, obviously, features that are going to be critical to make a machine learning model accurate. So exiting out of that process would be the model itself and then the feature definition. The next step is the model training phase. So this is where, again, the data science team is going to take the model they have and feed in real-time data in order to, and then test the model for accuracy. Right, so intuitively, we know that some of the features in that feature vector are going to have a greater impact on the prediction than others, right? And this phenomenon is sort of captured by what's called assigning a weight to each individual feature within that vector itself. So some things have a weighting of more, 3 times by 1, the other, etc. The goal of that model training process is to calculate the weight to assign to each of these features in order to get an accurate prediction. At the end of this model training process is you produce a trained model, which assigns different weights to each feature in the vector, right? So the output is a model itself, the feature vector, and now these weight vectors that are mapped 1-to-1 with the feature. So you know how much weight to assign to each relative feature itself. The process goes something like this. You select a subset of the historical data, carve that off and say, hey, this is our training data set. And then you feed it through the machine learning model and it generates some predictions. And then you can go back and compare that to the actual results. So in our case, we're going to say, we're going to take a set of orders and then compare what the average delivery time was. And then we have the actual delivery time because it's a transaction in the database. It says, basically delivered time, customer accepted time. And we can compare those results. And then we go back and say, okay, what was the accuracy of our prediction? Were we 80% accurate, 90% accurate? We have a certain threshold of mind we want to reach. And you keep doing that process and adjusting the weightings and maybe adding more features until you get the accuracy that you want. And it's an iterative process over and over and over again. So in our scenario, oftentimes, not just others, the goal is to have theoretically one model that handles all different use cases. But as you can imagine, there was just too much variance in sort of different factors that you couldn't get on a single model. And so what you'd have to do is generate what's called a suite of models for ones that adjust for the G's at different times of day or for different geographical regions, just because the weighting of those features are significantly different. So for example, traffic congestion patterns in different cities like New York, Chicago, and Los Angeles are going to be vastly different, as well as the time of day. Again, this is a food delivery application, and so peak meal times around breakfast, lunch, and dinner are going to have much different prediction times because of the busyness of the restaurants, et cetera, than things that are going to be at the middle of the day or on weekends and things of that nature, holidays, things of that nature. And so a way to address this is sort of have multiple models based on those different things. Have a model for New York during lunchtime, a model for Chicago at dinner time, et cetera, et cetera. And you can generate a suite of those models and keep track of when they are. So now let's look at the phase where Pulsar functions come into play. So we've done all the pre-work. That's all been done by the data science team and the data engineering team. Now it's time to look at our role as Pulsar function developers and how we can take these models, these trained models that have been given to us by the data science team, and put them to use in production use cases. So let's again take a 10,000-foot view of what model deployment is, right? And so basically you need to take they give you a trained model indicated by that yellow puzzle piece, which then dictates which execution engine you must use, right? So there's different types of models require different runtime environments. So if you have deep learning models, you could have a TensorFlow-based model, you can have an R-based model or a Pandas-based model which runs on Python, et cetera. So those dictate that model execution engine that you need. Each trained model also has a predetermined feature vector definition, as we talked about earlier. You know what inputs are required into that model in order to generate a prediction. And so that in turn dictates which data we need and how we have to go about going and getting that data. So those are our concerns are the model execution and the data access, filling in those pieces of the puzzle as model deployers. So why Pulsar functions are a good fit for this, right? So models can be shared themselves using Pulsar's internal state store. As I mentioned earlier, that Pulsar is a state store and you have a model suite. And so you can publish those things internally and hand off that model directly to a Pulsar function. And that's a backdoor way to sort of hand off those models. Pulsar functions can also leverage existing machine learning execution libraries, right? Any sort of deep learning for J, any sort of PMML evaluator, TensorFlow, et cetera. It supports a variety of plugins as long as there is a Java or Python or Go client for that particular machine learning execution environment, then you can use it inside a Pulsar function. Similarly, Pulsar functions can leverage existing client libraries to go retrieve the data. So any library or any data store that has an existing client library for Java, any sort of standard SQL, feature stores, things of that nature. The key value lookup pairs can obviously be used inside Pulsar function as well to go retrieve the data to feed the feature vector information into the model. So model deployment and machine learning model execution is basically at a high level a 4-step process, right? The first step is to retrieve the appropriate trained model from somewhere. As we'll see, if you have a model suite, you're going to have to rotate that model out periodically and switch it in and out. The next step is, once you retrieve the model, is to initialize an execution environment for that machine learning model. It needs a place to run. It has a specialized library. You have to get that environment up and running. Third, you need to retrieve all the data for the features defined in that feature vector. So you go look at the associated feature vector definition. You have to have a strategy for getting all those values into the model itself. Once you retrieve those values for the model, it's step 4. You then feed it into the model, execute it, and allow it to generate the prediction itself. So let's take a look at how that works inside of Pulsar functions, and my Pulsar function supports all 4 of those. So in the lower corner, lower right side, you can see the data science team develops and trains the model using the process we discussed earlier throughout the talk, right? They go through the selection, the training, they have a model that they think is ready to go. They can publish that to the Pulsar state store using a command line, which we'll see shortly. That automatically makes it available to any sort of Pulsar function within that same namespace, that it can then be fed to the machine learning execution engine. Now, based on the engine type, we know we can spin up the client and start that execution engine and feed that model into it so it's primed and ready to go. On the other side of that pipeline, we know the feature definition available, and we can have a separate pipeline of Pulsar functions that perform the feature collection process. Theoretically, you could do this in parallel to speed up the process, but they go and they query all the data sources and populate the feature vector itself, and then feed that in as a topic into the machine learning enabled function. And so it's consuming only feature vectors, which you can immediately feed into the machine learning execution engine, and the output will be the prediction around, in this case, the delivery time estimate, which will then be available to be distributed across the system and displayed to the customer, so on, and used to track that performance. So let's go into the details of that a little bit, one by one, step by step. So step 1, retrieve the appropriate model, right? Trained models can be exported in a transferable format such as PMML. That's a XML-based format, which we'll discuss in a little bit about how a format around how it can be exported. You can also use a binary format as well, or any sort of format, because it's really just a storage of bytes. Once those exported models can then be published to the Pulsar's internal state store, which the data science team says they're ready. Or you can have an ML operations pipeline, have it automated in some way that says, hey, these bytes are ready, this is the new model. And then that can be done, as part of the pipeline and scheduled again periodically. So as we mentioned before, we have a rotation based on time. And so once the breakfast hour starts, you can rotate it in the breakfast model or the lunch model. And that one's done, you can rotate it in a different one. Again, periodically, that can be done automatically, and it doesn't require code changes on your part. Right. So as we mentioned before, the data science team in this case, they used a linear regression model is what they chose, and they used an R-based notebook. Just an example to show you that we can support that or any other model. Right. By default, or they decided to export that into what's called a PML format, which stands for Predictive Model Markup Language. And that's just an XML representation of the model that includes its feature vector, its weights, the algorithm, etc. This is an example of what that linear regression model PMML format looked like. As you can see here, in the data dictionary section there in the middle, those are your feature vectors. You have difference, the distance, the meal preparation time in the last hour, the meal preparation time in the last seven days, things of that nature. Also, you're going to calculate the distance. It shows that it's a regression model itself, and it takes all these different values to calculate the value. So once that is exported to PMML, it can be just exported directly to the state store using a REST call or a command line interface that wraps the REST call, and you can execute the command shown there. So you basically do a put state command. You specify the name of the function, the namespace, and the tenant that's going to be consuming this. and then you put in a key associated with that. In this case, we use ML model, and then the byte value itself, which is the raw contents of the PML, or the binary model, or whatever you want to push up to the state store. That makes it addressable and accessible by the machine learning model inside the Pulsar function. So step number 2, inside the Pulsar function, you can then retrieve that value using a get command. There, you can see in the line, use the get state command from the Pulsar function context. In this case, the model key is predefined, so we use ML model as we used in the previous one, and we retrieve those values. Then we can immediately pass those values into a regression model evaluator, because we know it's a linear regression model. And using the library's built-in feature, it can parse that PML automatically for you, and then unmarshal the data, unmarshal the bits, and instantiate that evaluator object. And then that can be a one-time operation or triggered periodically when a model changes. You can go back and check every time that if initialize flag can allow you to check, can trigger if that event gets changed, you can trigger a flag and says, no, it's time for a new model. So now that we've done step 1 and 2, let's look at step 3. Separately, there's a sequence of Pulsar functions that can, again, execute concurrently in order to decrease the overall latency of this retrieval of the data. So once the features are retrieved, you populate the feature vector to publish the output topic, right? So it can be stored, the feature data should be stored in low latency storage, right? So you can have, again, we need to get the average meal prep time. You don't want to go against relational database to do that, because that can be very, not only non-performant, but you're getting in the way of your actual business operations itself. And then you want to put any sort of latency, or worst case, crash it and bring your business down. So you want to sort of store that data in a low latency data storage. And this is where you leverage the data engineering team to sort of pre-calculate these values for you and store it in what's called a feature store, right? And so this was highlighted in a recent engineering blog that Uber uses to describe how they use the feature stores inside their, they call Michelangelo machine learning platform. But basically what you do is you query that transactional database to pre-compute those values at regular intervals, right? So you go and you hit that database, or you have a copy, better off a mirrored image of that production database, where you can use primarily for these sort of analytical queries, and then you run those SQL queries we saw at the beginning during the data exploration. But rather than do it at real time, when you have the restaurant, you pre-calculate these values. And so now you can just do a lookup by restaurant ID and get all those values that you need, right? The average prep time the last 7 days, average meal preparation time the last hour. And these are in minutes. Their average rest rating might come to play as far as a feature you might need. These are designed to be very, very wide data structures, key value pairs you look up, and you can look them up very quickly. And so if you look at the statement here, we can do, again, that all inside of a Pulsar function, right? So in this case, we're going to retrieve all the different features for a restaurant. That's another values. We can pull all those values in one query. And then for our particular use case, pluck out the ones that we want and ignore the other ones we want. So in this case, it's you can see it's pretty standard SQL around querying the database. You have a predefined statement you want to do. The prepared statement uses one key itself. It's the key field of the restaurant ID. So the quick-ups are very quick. And then once you get the result set back, you just pull out those features that you want, and you publish them to the output topic. So you have everything you need in one shot. You don't have to hit multiple queries to do it, or hit run different statements. You get it all in one particular stop. One statement, boom, you're done. So now the last phase is, and that again, that happens in parallel. So the incoming data is then going to be the data that we want, right? And that's the food order ML there, shown as the first parameter into the process method there in the upper left. That is the data structure that we've stored those restaurant features into, right? And so now, again, we're revisiting there. We've loaded the model in that first phase that you saw earlier. We mentioned that. Now you have the model ready to go. You create yourself a feature vector struct, in this case, a hash map. And then you just start putting those values in, right? So you grab those, those field names, average meal prep time, you get it directly from that food order value lookup that you had there. So you go get the restaurant features, grab those out. You may have driver features, you pull those out. You may have other features. But again, it's all available in one shot. You don't have to go anywhere looking for it. It's right there, and it's just a simple copy, transcribe these fields into that map, and then you're done, right? You put them in there one by one, feed the data in there, and that's it. Finally, once you finish and put in all those different feature vectors into the model, into that feature vector, the final step is then to just call the evaluator, in this case, the execution environment we have, and say evaluate on this feature vector that populated. Here you go. And you say, I want to return the field I want to get back. In this case, is the travel time. So I'm going to predict the travel time it takes from given all these feature values for this particular driver. And then when I'm done, I just say, okay, on the output, I say, this is the estimated arrival time. Boom, that's the value I get, and we return it. That's all that's required in order to do that within a machine learning model function. So let's review. Covered quite a bit. Let's go back over what I've done. So I've presented a technology agnostic design pattern for deploying machine learning models inside of Pulsar functions, right? And this works regardless of the underlying algorithm or development language. And it consists of those 4 steps we talked about. You load the machine learning model definition into the state store. You can then initialize the model execution engine after you retrieve that model definition from the state store. You can retrieve the input data for the model using Pulsar functions as a separate pipeline, preferably from a feature store, so you can do it in real time or near real time lookups. And then you transcribe that data into a feature vector, and you execute the model against those values. And so they're a great tool for doing online operation because they allow you to execute those models near the source as the data is coming in on a per event basis. So when the food order comes in, you can go retrieve that data quickly from the event store, feed it to the model that's been trained with real data, and boom, get a very accurate prediction, and then feed it back to the customer and say, okay, it's going to be 23 minutes until you get your order. Pulsar functions also enable you to dynamically swap out trained models. The model that was deployed earlier, as you mentioned, so we have to rotate these models periodically over time. You can do that without any sort of code changes or downtime. So this is critical when you need to rotate these things periodically, or you need to support multiple versions of a model, right? So you have a Chicago-based model, you have a New York model, and then you have a time-of-day model. You can have different functions all doing the same, quote unquote, same base code, and all you change is the model inside, and that can be done dynamically. And again, Pulsar functions allow you to leverage existing data access clients. So any sort of Java, Python, Go sort of client library exists, you can automatically use that as well as part of your pipeline. And they also allow you to leverage existing machine learning execution frameworks as well. So that allows you to support the broadest range of model types, right? So you don't have to have any sort of limitations on the machine learning models that your data scientists use or create for you. None of their tooling gets impacted by you. Whatever they can do, as long as there's a Java or Python execution framework for it, you can support it with a Pulsar function. So the last key points I want to walk away from or leave you with is, in order to decrease the overall latency of the process, you want to again store your data in a low latency data store, like an in-memory data grid, like we do with the driver location data, as you saw at the very beginning. They're publishing data periodically. We put that in a memory data grid so we can grab that data in real time and don't have to sift through a large data store or data lake where we're storing that data. And the data engineering team should be responsible for scheduling periodic calculation of that data and storing it in that feature store, right? So that's their contribution to this whole process. Is once the data scientists have identified the features they need, they schedule this thing to be processed, using a high throughput processing engine like Flink or Spark or something like that, and store it in there. Again, so you can do quick lookups by restaurant ID, by customer ID, linear time operations, retrieve lots and lots of data. And with that, I'll see if there's any questions.